Throughout this video series you have been seeing graphs of polynomial functions. In this video we'll look at these graphs in more depth. Graphs of polynomial functions have certain features that are true of all such graphs. They also have features that are true under some conditions. Let's start with the common features. Polynomial function graphs pass the vertical line test. This is true of all function graphs. A vertical line will intersect a polynomial graph at only one point along the curve of the graph. Any graph that passes this test is a function. A second feature common to all polynomial functions is that their graphs intersect the y-axis at some point. This point is called the y-intercept. Recall that a polynomial function has this form. The a sub 0 term is the constant term. This term is the y-intercept. If a polynomial function doesn't have a constant term, then the y-intercept is 0. When that's the case, the polynomial can be factored. A monomial with an x term can be factored out. A third feature common to all polynomial function graphs is that the number of times a polynomial function intersects the x-axis can't exceed the degree of the polynomial. Let's look at this in more detail. When a function graph intersects the x-axis, we call that a root of the function. Let's start with a polynomial function of degree 0. The result is a horizontal line parallel to the x-axis, which will never intersect the x-axis. So the number of times a polynomial of degree 0 intersects the x-axis is 0. The only exception is the graph of y equals 0. This function completely overlaps the x-axis, which means that it intersects the x-axis an infinite number of times. A polynomial function of degree 1 is a linear function. If its slope is greater than 0 or less than 0, then the graph will intersect the x-axis only once. If the slope is 0, then it is a constant function and no longer a polynomial of degree 1. The graph of y equals 0 has infinite roots. A polynomial function of degree 2 is a quadratic function. Some quadratics don't intersect the x-axis at all. Other quadratics intersect the x-axis only once. Other quadratics intersect the x-axis twice. But there are no quadratics that intersect the x-axis more than 2 times. A polynomial function of degree 3 is a cubic function. Some cubics intersect the x-axis once. Others intersect it twice. And still others intersect it 3 times. But no cubic intersects the x-axis more than 3 times. A polynomial function of degree 4 is a quartic function. Some quartics intersect the x-axis once, some twice, some 3 times, and some 4 times. But no quartic intersects the x-axis more than 4 times. This pattern continues with all graphs of polynomial functions. Also, polynomials of odd degrees intersect the x-axis at least once. Here are a series of odd-powered polynomial graphs. All of them have one root, and in general all odd-powered polynomials intersect the x-axis at least once. In contrast, polynomials with even powers can have graphs that don't intersect the x-axis. Here are several even-power polynomials that don't intersect the x-axis. Now let's look at some features that aren't common to all polynomial functions, although they are also important to learn. Many polynomials have a roller coaster shape, with peaks and valleys. The highest point on these graphs is called the global maximum. Some graphs also include a lower peak, which is called the local maximum. Other graphs have a different orientation. These graphs have a global minimum and a local minimum. Now let's look at how polynomial graphs behave as the x values approach infinity. This is known as the end behavior of the polynomial. There are 2 things to look at: the degree of the polynomial and the value of the leading coefficient. Let's first look at polynomial graphs whose degree is an even number. These types of graphs have basically 2 shapes: one that looks like the letter U, or one that looks like an upside-down letter U. When the leading coefficient is positive, then the graph is a U-shape. Here are 3 graphs with even-numbered degrees. Each polynomial function has a leading coefficient greater than 0. The end behavior for all of them is positive infinity. Now let's look at even-powered graphs with a leading coefficient less than 0. These are upside-down U-shapes, and their end behavior is negative infinity. Next, let's look at polynomial graphs whose degree is an odd number. Since odd-power graphs always cross the x-axis, the end behavior will be that one end approaches positive infinity and the other end approaches negative infinity. Here are 3 graphs with odd-numbered degrees. Each polynomial function has a leading coefficient greater than 0. The end behavior for all of them is as shown here. Here are 3 graphs with odd-numbered degrees. Each polynomial function has a leading coefficient less than 0. The end behavior for all of them is as shown here. Notice that with odd powers the end behavior is similar, although the orientation of the graph is different. Let's put all that we've covered about polynomial graphs into an application. Let's design a roller coaster based on certain specifications. Suppose you want to construct a roller coaster that looks like this. Based on the graph shown, how can we reconstruct the polynomial function written as an equation? Start by looking at the number of roots. There are 3 roots, at x equals 0, x equals 1, and x equals 5. We use that to build the shell of the polynomial, which is the product of one monomial and 2 binomials. Next, look at how the curve behaves near these roots. See how the curve bounces at x equals 0? This is quadratic behavior. See how the curve crosses through x equals 1 in almost a straight line? This is linear behavior. See another bounce at x equals 6? We adjust the powers of the binomials based on their behavior to get this expression. There are 2 squared terms and a linear term, resulting in a 5th-degree polynomial, and the graph has the behavior of a polynomial of odd degree. Finally, let's look at the end behavior. What you see is consistent with a leading coefficient less than 0. With this final adjustment we have our polynomial graph. Test it out on a graphing calculator.